I'm going to be talking today a bit about how we've implemented at Quizio over the last roughly 10 months how to use Wolfram Cloud as an API type service to allow us to scale our business, to do lots of calculations. I'll describe what that means in words, continuously, and also to help accelerate how we develop algorithms, which we're constantly doing. Before we even get into that, though, one of the things I discovered over the last many years of doing this, and I used to give talks in like 2006 on using R with Mathematica and things, we were building systems that would separate certain computational complexity away from day-to-day operations. And one of the things that we certainly noticed right away, and it's certainly true in our calculations here, is a lot of times you can cast a calculation as something you're doing frequently, but has coefficients in it that are updated on a less frequent scale, like once a day, once every 6 hours, something like that. And so your system has two types of calculations. You have one, like we do every 30 minutes, which is update a bid we do at Google. So how much are we currently bidding at Google right now on that device and that campaign for that client? Those are done millions of times per day across our clients. But things that it uses, like what is the look back period that I'll do for looking at data? What is the CPC? What is the result of my bidding? What am I trying to pay per click across a day? Values like that change daily. They don't change every 30 minutes. And those type of calculations are examples of type 2, which is calculations which are much more complicated. So the first case is almost like a series calculation, like a Maclaurin series or something. A bit different, but same idea. And the second one is we're really using machine learning to determine what is the best result. It takes a lot more time to do those calculations, but still we have to do many thousands, 100,000 of these calculations a day currently, which can take a very long time. The second group are really good candidates for this technology. And so what we're hoping to do is we wanted to, one of my dreams I always wanted to do was leverage Mathematica libraries in a commercial sense, on a commercial scale. So how can we actually make use of these and not have to rewrite all of our code, as I'll describe in a minute? That helps us really speed up our testing and things that we're doing. So it allows us to, as point 2 says, decouple the algorithm part of our business away from the rest. Because one of the things we're most afraid of is, and I've always seen this in my work that I've done over the last almost 25 years, I've used Mathematica 26 years, this is 1990, version 2, is that I'm always afraid of having somebody rewrite my math who doesn't understand math. That's a very scary thing, and lots of weird errors can come up in your code when they do that. So, I've been living with this my whole life. So, what this allows us to totally decouple it. So we have our scientists write the Mathematica code, it goes directly from concept to production without being rewritten. And then the scientists, computer scientists, write all the rest of the plumbing that connects to that. So it keeps the right actors doing the right jobs. And it greatly expands our ability to test in production. That's really a challenging thing. One of my first revelations in AdTech, internet advertising technology in 2005 when I was working with Right Media, was we waited for a data drop from this company for almost 6 months after signing our contract. And we were going crazy. We don't get paid until we do work. So we're waiting and waiting and waiting. And as the CTO said, Bryan O'Kelly, who's now the CEO of AppNexus, a very large ad tech company out of New York, it was like changing airplane engines with an airplane in flight, getting the data out of it. Very hard to do. The reverse approach to that is you test in production. You need to test your algorithms in production. That's the only place you do real testing. So it's like split stream testing. So you have to have an ability to test many, many algorithms across many, many test groups, all in parallel live. You can't do things in the development environment, make-believe environment, that are meaningful. You can pull data from Google or Facebook or Bing. You can look at it and act like you're doing calculation, make sure all that plumbing works. But at the end of the day, if you don't actually do a bid, you don't know what happens in the auction. You don't know if your technology actually works. So the architecture we came up with, which we think is a solid design is that we divorced our algorithm work away from the rest of the company through a RESTful API. Everything we're doing on the algorithm side is totally stateless. So they package up the data, they hand it to us, we do the calculation, we hand them back the answer, we forget about it. A lot of good things come of that. Horizontal scalability. We can scale out infinitely horizontally. There's no problems with that at all. It's the ultimate example of stupid parallel. We defy Amdahl's law in that regard. And it lets us work independently. So it doesn't matter what language you write in on the right-hand side. We write in Mathematica, Wolfram language, but we could write in some other language, R, Python, make up a language you like. And they can do what they need to do on their side. We can talk to each other through a standard API. We can also, therefore, deploy asynchronous to each other. And we don't have to worry about all of the data persistence issues that invariably come up. This is our traditional development cycle before this project. I'll go through it real quickly, but we come up with algorithm ideas. We do that all the time. They say at Google that they do 2 algorithm changes a day on average for Google search. 2 a day. About 600 and some odd a year. How do they do that? Well, they don't do this. That's for sure. They do not do this. Because what happens here is you come up with an idea, you have to document it. Oh, excuse me, this is the wrong slide. I'm ahead of myself. That's fine. I'll jump to this one. You come up with an idea, you prototype it in Mathematica, you create documentation, your team can review. You've got to have people reviewing the ideas, make sure the science is right, the science team reviews it. And then you do the investment of designing software documentation now that the non-scientists can use to build the scientific software. That takes weeks or longer. Then you have to implement it in some language, not Mathematica, not Wolfram language. That takes months, usually. Then you have to test it, which takes another month, and make-believe testing, dev. Then you have to test it in production, which takes weeks or months. And then if you see something is wrong, there's no easy reverse path in most cases. You can turn it off. You can maybe roll back to the old algorithm, but it's a very painful path in most cases. And QA testing is very difficult. Look at how we're doing it now. We skipped that whole part about reinterpreting our work. We write it once, we document it, we come up with our ideas. We then deploy them into a dev environment using the existing API. So we're totally asynchronous in normal development cycles. We have an existing API that's understood. We can deploy hundreds of algorithms against that one API. And all we have to do to deploy it, once we're convinced that it works reasonably well in rack testing, which means it can read, when we want to actually start bidding on auctions, we deploy it to some limited number of people, like 1 campaign, 10 campaigns. But all we have to do to deploy it is just change the endpoint in the database, so what we're aiming at. That's really powerful. So let you very quickly scale out from an initial start and let you see that whether it's working or not correctly. This allows you to very quickly, if you have a problem, turn it off. Just roll back to the other algorithms, takes database change. You don't have to redeploy code or undeploy code or deal with all those issues. And you can do very limited testing initially, as mentioned. What types of problems might one use this for? Here's a couple on I'm going to list. I'll do this real quickly. Look back. This is where we calculate, when we do our work, like on bidding, how much we want to bid at for a given auction in a given moment on Google, let's say. We're looking at it for different devices, mobile, not mobile, so tablet, desktop. Every campaign has their own, and device has their own look back, and it can be as short as 3 hours, it can be as long as 48 days. Do that for everybody. So we have hundreds of thousands. These we're calculating every, let's say, day. That's a good example of one of these calculations. So what are we actually targeting for what we're trying to pay? CPC, cost per click, across these devices, across campaigns. What's your daily budget? How does it vary with campaign? How does it vary with the group of campaigns that are sharing it? How does it vary by time of week, time of year? This is a complicated calculation. There is machine learning involved. Then we have all sorts of things we do regarding analysis. We're looking at people's actual ads and seeing what are they advertising upon. Looking at their keywords and seeing what they're really advertising upon. I'll show an example of that. It's a great example of clustering, machine learning classification problem. But you have that across tens of thousands or more examples you could do it upon. And then, of course, analysis that you're ongoing. Here's live data from a couple days ago. This is one of our bigger algorithms. You can see here, this is Mathematica stuff I actually used for the first time, one of these. So this shows the pop-up there that we're doing 46,000 and change API calls on the 10th of October for this particular algorithm. That's quite a few. That's about 1 every 2 seconds. And it's just one of many that we do. I'll do something here to make this a little bit easier to see, I think, maybe. This shows in every single day what, for the whole round trip experience, what was the mean execution time. So it's roughly 1.4 seconds. Standard deviation, 1 second roughly. Shows that varied in time. We did an Oracle database upgrade here, which made it worse. There's some load balancing issues. Right there, you can see the Oracle database change. To the right here shows actual within Wolfram Cloud land what we're actually doing. You notice it's very, very stable. Even as we double, triple, so forth, our load, the actual computation stayed pretty much the same. So this is the mean time to do an execution. It's roughly a half second, 650 milliseconds. And the standard deviation is about half that, which is a really good result. Sort of surprising. This is on an 8-core machine up on AWS with roughly 64 gig of memory, running 8 Wolfram kernels on it. But a big part of that is threading. One of the biggest things we discovered too early on, which is no great surprise, but it's nice to verify, is that we get really good pipelining. So as we load up the queue with many, many jobs through threading, that the servers are not next to us makes no difference at all. It's a big vector pipeline. So you just load it up, and that transit time between where we're at in Montreal and where the servers are at in New Jersey is like 0. Net effect on the results. There is no price that we see at all that we're paying. We run other cases. This is a very small example of a trial here. We're only running on, looks like 16 campaigns here. This is a very early one that we're looking at. And so it allows you to look across the system. Here's a Bing examples. Here's, I believe, 20 some odd thousand jobs they're running. And we do see when we went to Oracle on Bing that they suffered more. It's roughly 1.3 seconds, 1.25 seconds. And as a standard deviation, it's very similar to the other one. And this is related to load balancing and so forth. But once again, the Wolfram performance is impeccable. It's really sort of shocking when you see that much growth. You're going here from basically nothing, 1,400 to 20,000. That's a lot of growth. That's sort of crazy. There's one more example I list here just for completeness, but it's smaller, YahooJapan. So this is another client we have. We work with one of the largest ad agencies in Japan, and this is a small sample of some of the stuff we're doing with them. Right now we're doing roughly 100,000 of these a day, computations, calls to the API. That's roughly 3 million a month. And it's going to grow by about a triple in the next 3 months, roughly. Which graph? This one here? This is good news here. This is good news.
No,
Means that.
That was like in July, basically, you had execution time. Twice as now, despite the fact that you almost have no load. Is that something?
It could be load balancing, it could be configuration related. We did upgrades to the system about then. I also don't get excited about 2,000 jobs. I care about 30, 40, 50,000 jobs. I mean, sometimes with this type of thing, it's so noisy that you're just being misled by it's not really a feature. Yeah, I mean, I worry more about these type peaks here, but there's a hierarchy of publishers, as we call them. AdWords, Google, is by far the best. The response time when you call their API is about 100 milliseconds, something like that. Then you go to Bing, relatively speaking. Bing is 6 times slower per call, which is horrible. And then these guys are like 5 times slower than that. So they're like 30 times slower than AdWords, or 40, depending upon the day. It's ridiculous. I shouldn't say more, I'll get in trouble. But it means you have to use a lot more threads, it means you have to use a lot more scaling, it takes more hardware, it's just scary. And we talk to them all the time, and I'm not sure we're making any progress. Of course, Yahoo owns them. Well, enough said there. They're being chop-shopped, so they're being sold to somebody. These are examples. I just want to show a few examples of the type of data that I look at every day off of these results. This is what enables us to do this. One of our biggest jobs is to, almost like I joke about, it's like the Matrix. So one of my jobs every day I spend 3 hours on or more. I look at the data and look for things I can't explain. Look for small screw-ups. We meet every day for an hour. My team and I do, it's 4 of us that work on this specifically. Looking for mistakes or phenomena that just don't make sense. And then I want to make it better, or I see opportunities to make it faster. A lot of incremental changes cause big changes in cumulative. That's exactly what Google's doing and everybody else. Here's one graph here that's sort of easy to understand, which is looking at, it's a double graph, so it's showing on the y-axis on the right is clicks, which is the red shade I'm pointing at, so there's 9 clicks here. And on the other axis, the left axis, is what you're paying. This is cost per click. You ideally want to see clicks go up, costs go down. We call it an X graph. That's in a perfect world. This is a small account, as I'm mentioning here. So they're getting 9 clicks, 2 clicks, 3 clicks. It varies day to day what they're getting. We're varying our bid throughout the day. We're looking at all sorts of performance. We're looking at here, the blue is what we paid on a given day, CPC. The green is what we were trying to pay, as we call it the Skynet target. I like that term. Anyways, Skynet is the master of our software. The red is what we're bidding. The black is a constraint. We don't want to pay more than that per day on average. We have all sorts of job information about when we were sleeping, when we were doing smart work, when we were turned off, when we were day parted. This is actually green is what we paid, and black is what we wanted to pay. And so forth and so on. Monthly budgets, how many campaigns are running down here. This is sort of a cool graph here that I'm pointing at, which is sort of, when you get to smaller campaigns, they become almost like quantum mechanics compared to Newtonian physics. When you get really big accounts, you don't have to worry about how many clicks you're getting. It's sort of a continuous function. When you get to small accounts where they're only getting 3, 4, 5 clicks a day, you have discrete states. You don't get all. You don't get 3.5 clicks. You get 2, you get 3. You might get 4. If you go from 2 to 4, that's a 100% change. But it varies, it bounces around. There's a lot of, we show here in color, rainbow colors, the newest ones are violet, and the oldest ones are red, and then there's rainbow colors in between. So you can look at it and see what's going on. All of this is in support of what we're doing, so we can understand what's going on. We spend a lot of time on these graphs, this dashboard, as it enables us to do our work really well. This is all Mathematica. We're constantly making changes to it. What if we do this? What if we add this feature? All these lines you see on here tell us, like the green is when they change a constraint, the black is a change to budget, so forth and so on. Blue is they change the number of campaigns they're currently using. This is a much larger account. This has 700 campaigns in it. Sharing a budget. That's a lot bigger than the last one, which had 1, basically. So it's a very different type of result. And so we want to be able to handle all these cases with the mathematics that we're doing. We look at it different ways, like this. This shows red line is before us, to the left here in this graph. You see each month they ramped up their spend per day, which means they were not spending their budget evenly throughout the month. That's a bad thing. I call this the shark fin, that big black peak there. And just like running middle distance running like the great runner Prefontaine, even pacing is best. You don't want to spend all your money on the last day of the month You don't want to run out of money early. You want even pacing throughout the month. Very hard to do on smaller accounts. Very hard to do in bigger accounts. That's something we're looking at here. And then another thing we did recently, which I threw this in for the fun of it, I really like this. This is fairly new research. This is greatly benefiting from Wolfram Cloud because we can scale and go out and do this on everyone. We have hundreds of thousands of campaigns we do this upon. So we look at each campaign and we can look at all of its keywords and all the words they use in their ads and say, what are they talking about? We don't know anything about these people. They might be categorized by the advertiser, Yellow Pages, somebody like that, but I don't want to trust their. And there's different types of things you advertise upon. Some things, dentists, are not seasonal. They just occur all year, like lawyers. Other things, lawn care, they're seasonal. So your advertising won't be constant throughout the year. It'll be peaky in the summer and almost none in the winter, particularly if you live in Wisconsin or Montreal like I do. This is a case where we train on a training set across a reasonable number of campaigns, and then we went out looking at the rest of the data and said, with Wolfram Classifier, and said, what do we see? And for this case here, we can see we didn't know who these people were. It said something like, it sounded like a resting home is what I thought when I read it, but I didn't know. You can see they're doing mainly physical therapy, then they're advertising on nursing, rehab, psychologist. We have some unknown block. There's some keywords we don't know what they are. Might be junk. This enables us then to compare them to other people of like kind. It's almost like a 23andMe DNA test. So now we can tell what you are, and we can then compare you like kind. Something we couldn't do without the Wolfram Cloud. We're going to do this regularly on our clients, because we never had this information before. It is a good example of what you can see, and that's different with this type technology versus previous technology. You know, people say, well, with big data projects, you just get more of the same. Well, not really. This isn't anything we've seen before. Conclusions. We're able to implement algorithms now 3 times as fast as before. That's a pretty big deal for us as a company. We can significantly increase the number of algorithms we're testing and supporting. Before, in many of our algorithms, there was 1 or 2 maybe on a good day. Now we have like 5 or more we're testing. And so much of this that we do, we can't do it in any place other than, like I said before, production. There is no other environment. We've actually gone to the way I describe it now within the company. It took almost 3 years to convince our company of this, that it's sort of like F1 race cars. There's rack testing and there's track testing. You can test a certain amount on the rack, but you got to put the car on the track and see how it actually does. That's true with us. We have to actually bid. Actually, I actually had to be in the auction to see what's going on. Point number 3, we've been able to eliminate the non-mathematics issue. I think that's a big problem for a lot of companies. This totally separates the 2 activities. Scientists do the math, computer scientists do the computer science. That's great. I don't want to do that other stuff. I'm happy to give it up. Never really wanted to do it. Let's just leverage Wolfram language, mathematical libraries in production. That's amazing. I mean, we took, like the classification thing we showed there, our first cut on that we had within a few days. Done all sorts of analyses. We're looking to go, what about this? I mean, go test the idea really quickly with Mathematica notebooks and see what's going on. It's really been a great thing. It greatly extends our post-analysis capabilities. That's what I showed a few minutes ago, all those graphs. We're doing that across thousands and thousands of cases. You couldn't do that one by one. It'd take forever. And it decouples most of the complex computations away from normal software cycles. And that really is one of the key findings here. And lastly, it enables us to scale with the Wolfram Cloud and with AWS. There's a feature in AWS, some of you might have heard of, called Spot Market, where you can go out and do bigger computations for 1/10 the price. But you have to agree to certain things, like they might just turn you off for the fun of it, right in the middle of it. But it's 1/10 the cost, so maybe you do want to do it once in a while. And you can scale out and so forth as needed. Lastly, I just want to throw this in front of you. This is a recent Gartner chart. And it shows pretty clearly that people are looking at this issue. Particularly if you look at right here, algorithm marketplace. API-driven offerings like this are what's going to drive a lot of good science across particularly the business industry. This is from, I think, June, something like that, this year. And we're at the beginning of the hype cycle, which is sort of interesting. And what's also interesting, if you actually look at all these things they list here, you can discover that 2/3 of them benefit from this technology, or more. That's it for me. Any questions? Thanks.